Okay, hello, how are things everyone, and welcome for joining into this. Today's lesson basically is going to go over some of the homework that we had there for this week. Basically, it was exam paper questions based around, say, some of our geometric proofs for your angles and your circles, similar triangles, and say transversals and triangles as well. So we had, I think, 4 or 5 years there with maybe 5 questions. So the first one that we're going to look at is from the 2019 paper, higher level question 12. And basically it was a proof. So we had to prove basically that the exterior angle in a triangle is equal to the sum of the opposite two interior sides. Okay, so following from that, right, so you have to first, you have to state a diagram, give a diagram, you have to then state what you're given, you state what you have to prove, and then you do the proof. So first of all, the diagram that will go along with this. Okay, so we're just going to start, we have a triangle here, and we're just going to extend the base of the triangle out. Okay, so we're going to then mark in the three angles, and we'll just call them 1, 2, and 3. And we'll call this is our exterior angle here, and we're going to call that angle 4. So that is the diagram that we would be given. Okay, what do we, so that's diagram. Then given is basically the triangle, if you want to call it ABC, or the triangle here, and this straight line, so we'll label them up. So A, B, C, and D. So what are we given? So we're given the triangle A, B, C, and the ray line A, D. Alright, so you're given the triangle, and we're given the straight line AD. What are we asked to prove? We're asked to prove that the angle 4 is equal to the sum of the two interiors, so angle 1 and angle 3. Alright, so that's what we have to prove. We have to prove this exterior angle, angle 4, is equal to the sum of the two opposite angles on the interior of our triangle. So what does our proof look like? And it's one of the nicer, more straightforward proofs that you have to come across. Okay, what do we know about a triangle? We know that the three angles of your triangle add up to 180 degrees. What do you know about a straight line? Well, you know that a straight line will have to also add up to 180 degrees. So that's the start of our proof. That's how we prove it. So the angles 1, 2, and 3. So this is our proof here. So angle 1 plus angle 2 plus angle 3, they all added together equal 180 degrees. Angle 2 and angle 4 together, they make a straight line, which is also 180 degrees. Okay, so in a triangle, three sides added together give 180. A straight line, these two angles add also to give 180. So if these three add to give 180, these two add to give 180, both of them equal 180. So what I can do now is I can sub out the 180 and sub in the angles themselves. Okay, so instead of letting this top one equal 180, I'm going to sub out that 180, and I'm going to sub in these two angles here, because both of them are also equal to the 180. So I haven't changed anything, I've just subbed out the 180 degrees, subbed in these two angles, because I know these two angles also add to 180. So that's what we're going to do on our next line. Okay, so we've got angle 2 and angle 4 equals angle 1, 2, and 3. Now, I can see I've, on the left hand side of my equation, I have the angle 2, on the right hand side, I have also angle 2. So what I want to do here is I'm going to subtract angle 2 from both sides. So subtracting from the left, I also subtract from the right, and they are going to basically cancel. So then what I'm left with is angle 1 and 3, and that is equal to angle 4. And this here now is that theorem proved. The sum of the two interior angles, angle 1 and angle 3, angle 1 and angle 3, they add together and they equal angle 4. and angle 4 is our exterior angle. So we now have proved that the exterior angle of a triangle is equal to the sum of the two interior angles. And there it is, proved. And that's it. There's nothing else to do with that. There's your diagram. There's what you're given. There's what you have to prove. And that's the proof. Okay, so next question that we're going to look at is from the 2017 higher level again, and we're going to start with question 2. So there's two parts of this, an A and a B, and the first part is basically a line segment. We're given AB and we're asked to divide that line segment into 3 equal parts. Now I don't have set squares and equipment, all that, so I'm just going to do it freehand. Okay, but how do we go about it? So from either end of your line, we're going to put another straight line at any given angle. Okay, so I'm going to take a straight line there. I don't care this angle in here, as long as it's straight. Alright, and it starts at either start or end pointing of the line. Along this line then, I'm going to measure the number of equal parts that I have. So with a ruler, you would step out 3 equal spacings here. And then you would label them. 1, 2, 3. Okay, what you do then is, with a straight edge, you join your last point to the end of your line. Okay, that creates an angle. Then with your sliding set square, so putting one set square here, put another set square along the bottom, and you would slide the first set square along the second from point 2 and point 1 also. Right, so just keeping that angle roughly as it is. There, something there like that. So that's a third, and a third. Okay, so we've divided now our line AB into 3 equal parts without measuring it. Okay, so again, you would use your technical graphics equipment there, or your small little mathematical set squares for that. Okay, part B, we're given this rectangle ABCD, and the DC and BA is divided into 5 equal parts, top and bottom, and we've got a section in the middle. Alright, and we have to work out basically the percentage of the shaded area. Okay, so how much is shaded either side of this blank bit in the middle. Alright, so that's what we want to figure out. Yeah, it is shaded. Okay, so we want to basically find the percentage of the 2 bits in red added together. Alright, so if we take and we look at this, right, we have a rectangle. Right, we're talking about area. Can we get the area of this rectangle? That's the first question you need to ask yourself. We're given no measurements or no lengths, so how are we going to take and work out the actual area of that? Do we know from any other part of the course in maths where we've maybe given a value to some unknown number? So if I look at the line AD or BC, could I call that a given length? I could. We might call it X. So whatever it is, X centimeters, millimeters, inches, feet, whatever it is, it's X long. Okay. Looking from A to B and D to C, could I do the same? Bearing in mind that these 2 lines are divided into 5 equal parts. Alright, so there are 5 parts of something. So there's 5 of whatever length they are. So we could call them, you could leave it as 5, but we'll call it 5y for the time being. Okay, so the length of that is 5 multiplied by y. Okay, so up on the top here, we have a y, y, y. Alright, so we have 5 y's, and y will be whatever length it is. I don't care what length it is. All I know or want to know is that there's 5 of them. So the AD and CB is X units long. A to B is 5y units long. Alright, so the area of the triangle is length by breadth, so it is X multiplied by 5y. So the area of is equal to 5xy. Alright, so the overall rectangle, now I've been able to work out the area even though I wasn't given any actual lengths for it. So next thing that we want to look at is, can I get the area of the two shaded bits in red? So we'll deal with this side, the right hand side first. What type of shape are we dealing with? Well, it's an unusual shape, right? But can we make it into a regular shape? If I was to drop a line down here, can I divide that shape now into two regular shapes? Well, I can. I've got a rectangle and I've got a triangle. Okay, so what's the area of this part of the rectangle here? Well, we know that the height of the rectangle is x, and we know that the width of it is y. So the area, so we'll put this in red. So the black is the overall rectangle, red is for the area of the shaded bits. So first of all, this rectangle here is x by y, alright, so it's just xy. What is the area of this triangle here? Well, I know that from here to here is x, here to here is y. How do I get the area of a right angle triangle? Half the base by the perpendicular height, alright. So we're going to add on to this rectangle the area of this triangle. So half the base, which is x, or you can call it y, but basically it's going to be a half x y. Alright, half the base multiplied by the perpendicular height. That's the base, that's the height, x by y multiplied by a half xy. So overall, the right hand side is equal to 1.5 xy. Can we do the same over on the left hand side? We can. Divide it up into a given shape that we can easily work out. Well, again, we've got a rectangle here, alright, so x multiplied by y. Can we get the area of this rectangle here? Well, this is x by 2y. So x by 2y is 2xy, but remember, multiplying by a half, so it's just going to be xy. So the overall area of the shaded parts here is 1, 2, 3.5 xy. Now we've already worked out from the start that the overall area of the rectangle is 5xy. If the shaded part is 3.5 xy, how do we work out the percentage area? Alright, well, we simply create a fraction and we put 1 all over the other. Alright, so percentage, I'll go back to back. Percentage of the shaded part is equal to the shaded part all over the original. So 3.5 all over 5. Okay, and we're just into our calculators. Which is 70%. Okay, so the key to this question was actually working out the area even though we weren't given any measurements. Alright, so we had to take into account that this would divide into 5 equal parts, so it was 5 of something. Call it the something whatever you want. We don't know this, call that something else. So this I call x, I call these y's, and work it out for the area of the rectangle length by the breadth. For the shaded parts then, break your shape down into regular shapes there that you can easily work out the area to. Get the area of the whole shaded part, compare that to the area of the overall rectangle, but the shaded part all over the larger part. Now I dropped my xy here because I'm only looking at, well, how many times bigger or smaller is the 3.5 compared to the 5? And that's all you had to do for question 2. Now I think the next one there is also from the 2017 exam paper. It's question 12. So I'll just pause until I wipe away and get rid of it. Okay, so for the next question, it is question 9 actually, rather than 12 out of 2017. Now there's a lot of text in this, so I'm just going to hold that up to the screen and you can maybe pause that and just have a read of it through yourself, or I might be, when I'm editing the video, I can actually include an image of that to the side. So basically what we're talking about here is we have three terms, all right, and we've got three statements, and we have to match each statement with the particular term, all right. So if we look at our statements, or the description of each of them first. So first one is a statement that is accepted without proof. We have then a statement that follows easily from a previous statement, and the last one is an argument showing that a statement must be true. So we'll start from the bottom up. So an argument showing that a statement must be true. So basically we're stating something, or we're proving something via some means. So the last one there is our proof. Okay, we look then at the last two, or the remaining two. A statement that follows easily from a previous statement. Okay, so we have taken something and we're developing a bit more. So we're using what we've already done to state something else. All right, so that is what we know as a corollary. And the last one then is our axiom, a statement that is accepted without proof. So an axiom is something that we just take for granted as being correct. All right, so we have axiom, corollary, and proof. Okay, so part B then, Salem writes the following statement: if a shape is square, then it must have four right angles. Complete the converse of Salem's statement. So basically the converse is the opposite. All right, so if a shape is square, or is a square, then it must have four right angles. So basically opposite to what he said is, if a shape has four right angles, then it must be a square. That's basically the opposite of what he has just said. So that's what would go in there. So if a shape has four right angles, then it must be a square. So moving on to part two of that, is the converse of Salem's statement true or false, and justify your answer? Well, it is false, because we know that a shape that has four right angles doesn't just have to be a square, it could also be a rectangle. Okay, so that is for A and B. Moving on to part C, we have a proof. Basically, we want to prove that opposite sides in a parallelogram are equal in length. So we'll start off with that. Okay, so again, just first, we're on, what did we say, we're 2017 question 9, and this is part C. So basically what we're looking at is a parallelogram. So first of all, we draw in our parallelogram as best we can. So there is our parallelogram. We'll make it a bit better. Okay, so there's the diagram, right? And what we do is we include a diagonal line joining these two corners or those two corners. We just go with these ones here as best we can. Okay, we'll call that fairly close enough. All right, so that's the diagram. Okay, so that's the diagram that you have to sketch and include in. Now we will label parts. So what I'm going to do is I'm going to label the angles. So 1, 2, 3, and 4, and we're going to label 5 and 6. I won't bother. Right, and then I'll label the overall sides A, B, C, and D. So there's the diagram. All right, and what are we given? We're basically given your a parallelogram. All right, A, B, C, and D. So that's what we're given. We're given the parallelogram A, B, C, D, and we have to prove that the opposite sides are equal in length. So basically I want to prove that the length AD is equal to the length BC, and also that the length AB is equal to the length DC. So that's what I have to prove. Right? So how do I actually go about proving that or constructing that? Okay, well, we know that in a parallelogram that we have parallel sides. So we know that DC and AB is parallel to each other. We know that CB and AD are parallel. So using that fact, we can say that the angle 2 and the angle 4 are equal to each other. Why? Because they're alternate angles. We also can say that angle 1 and angle 3 are equal to each other, again due to the fact that we have alternate angles. We can also say that the length of side AC for this bottom triangle and the top triangle AC is common to both triangles. So what we want to do basically here is we want to prove that this lower triangle and this upper triangle are congruent to each other. Alright, how do you do that? Remember, we had 4 cases where we had to prove, and we're going to use the fact of two angles and a common side. Okay, so you have to state that. Alright, so we're going to say that angle 1 and angle 1 is equal to angle 3. Why? Because they're alternate. Alright, similarly, angle 2 and angle 4. You're going to forget how to write when you're not doing it that often. Right, also then, the side AC is common. So, what have we done? We have now proved angle, and a side. Okay, and that is one of the ways that we can prove. So, what is that? ADC. So we have proved now that both of these two triangles are congruent, so basically means that they are equal to each other, because we have used the fact that side, angle and side are equal in both triangles. So this angle and that angle are equal, this angle and this angle are equal, and then this is a common side between both of your triangles. So we have now proved that this triangle and this triangle are congruent, or basically are the same, just different way of drawing it. And from that, right, so that is our proof. So from, if you look at the section part A, which are our proof, our axiom and our corollary, we can now take and lead on, because these two triangles are congruent, right, we're using an axiom here, we can now state that opposite sides have to be equal as well. Okay, so that now we have proved that the angle, or the length should I say, of side AD is equal to the angle, or the side should I say BC, and the length. Okay, so by proving that these two triangles are congruent, we're able to prove that the length of the sides of opposite sides are equal in a parallelogram. That's all we were asked to prove in this question, but you could go take a step further. You might be asked to prove that opposite angles are equal. Okay, so if angle 4 equals angle 2, and angle 1 and 3 also equal each other from what we have up here, because the two of them are alternate angles, then 4 and 3 added together is the same as 1 and 2 added together. Okay, so now that angle there and that angle there are equal. So we can also prove that opposite angles in a parallelogram are also equal. Now, you don't need that for this particular question, but you can also be asked that in this particular proof. So in this case, we were just asked to prove lengths of the opposite sides are equal, but you can also be asked to prove that opposite angles are equal as well. Right, so we're moving on now to the 2016 paper, and again, we're a higher level, paper 2. And it is, what did we say, question 6. So again, sticking with the theme of proofs, this time what we want to prove is that any triangle, that the 3 angles in that triangle would add together to give 180 degrees. Okay, so that is, again, another fairly straightforward proof that we have to do. So what is the diagram that will go along with that? Right, start off, draw any triangle. Alright, and include then a parallel line to the base line here. Have that parallel line go through the vertex of this top of your triangle there. Alright, how do I know that they're parallel? We put a little arrow and a little arrow. So we know that the two lines there, call that maybe line L, and this line here are parallel. Now I want to name my triangle, each vertex A, B and C. What I'm then going to do is I'm going to label my three angles within the triangle. So angle 1, 2 and 3. And finally I'm going to label the two angles either side up to the straight line, and I'm just going to call that angle 4 and angle 5. Okay, so that is the diagram that goes along with proving that the three angles of any triangle add to 180 degrees. So that's the diagram, right? That's what we're given. So you're given triangle A, B, C and your straight line. So you're given your straight line L and you're given your triangle A, B, C. That's what you're given. What do we have to prove? We want to prove that angle 1, angle 2 and angle 3, when all added together, will give 180 degrees. Alright, so what does the proof of that look like? Okay, well, if we think back to our little bit on geometry and we look at, well, we've got two parallel lines and we've got a third line cutting each of those. Well, we have now created a series of alternate angles. So we know that angle 1 and angle 4 are equal because of alternate angles. We can also say that angle 2 and angle 5 are equal because of alternate angles. So that's the first thing. So angle 1 is equal to angle 4. Why? Because they're alternate. We can say the same is true for angle 2 is equal to angle 5. Alright. Straightforward enough, there's nothing too taxing on that. Alternate angles due to our two parallel lines. We have got a straight line. Well, I know that angle 4, 3 and 5, if I was to add those together, what's the angle of a straight line? Well, it's 180 degrees. So angle 4 plus angle 3 plus angle 5, they all add to give me 180 degrees. If angle 1 is equal to angle 4, can't I replace angle 4 with angle 1 and I want to change what I have? Can't I do the same with angle 5, replace angle 5 with angle 2? So that's what I'm going to do. Because each of those is equal, so by subbing out angle 4 and subbing in angle 1, I haven't changed anything. The two of them are equal, the two of them are the same. So replacing angle 4 with angle 1, we're going to get angle 1. Keeping angle 3 where it is, and then replace angle 5 with angle 2. That has also got to be equal to 180 degrees. The reason being is, if this is equal to 180, and if 5 is equal to angle 2, and 4 is equal to angle 1, this all three together give 180, so by replacing them out, it also has to still add up to 180 degrees. And that's your proof that goes along with proving that any triangle with three interior angles add to 180 degrees. Okay, so moving on then again to the 2015 higher level paper 2 exam, we're going to look at question 7. Okay, so this is to do with a set of triangles and basically similar triangles. Alright, and we have to prove or work out basically the value of x and also the length of BC. So what information are we given? We've got a triangle ABC. Within that we have a smaller triangle ADE. On both of these lines we can see that there's two arrows, so that is telling us that each of those lines is parallel to the other. Okay, So that's an important fact that we're going to use in the second part of the question. But if we look here for part 1, we have to find the value of x. So you can see in this smaller triangle, we've got 2x here, 3x, and we don't know what this is. But we also know that over here, this angle is 70 degrees. All right, what do we know? If this line CB and DE are parallel, then this angle and this angle are equal because they're corresponding angles. All right, so I'm going to put that in here. This is also 70 degrees, corresponding angles. Okay, so now what do we know about the smaller triangle? We know the 3 angles add up to give 180. So 180 degrees is equal to the sum of the 3 interior angles. So we're going to get 2x plus 3x plus 70 degrees. All right, so add all those together. So we're going to get 5x is equal to 70, plus 70. Okay, I'm going to subtract 70 from both sides. So I'm going to get 110 degrees is equal to 5x. Okay, so I'm going to get that dividing both sides now by 5. I'm going to get 22 degrees is equal to x. Alright, so I simply divided 5 into both sides. So we now have worked out what x is. X is 22 degrees. Moving on now. So maybe pause that and just look and get that happy in your heads. Moving on, we want to find basically the length BC. So that side there. So what we're using basically is our similar triangle method here. So we just put a line under this here, and remember back from when we were looking at the theory of this, what we were saying is it's to do with ratios where we have 4 bits of information where we know 3 and the one that we don't know is the one that we're trying to find. So we'll call this, rather than call it x here, we'll just call this y. Okay, so we're going to create a set of ratios. So if we look at this side of the triangle, from A to E, I'm told is 100. From A to C is 130. Okay, so we've got our small triangle, we've got our larger triangle. We know 2 bits of information that is both the same side in the similar triangles. Alright, ED we know is 74. The corresponding side in the larger triangle is CB, and that's the one that we're trying to find. So we're looking at corresponding sides in our similar triangles. So whichever you want, you go largest or smallest first. We'll go with the smallest first. So I'm going to go create 2 sets of fractions. So one of them is equal to the other. All right. And on this side here, I'm going to have the smaller fraction here of AE, which is 100. And that goes all over 130. All right. So it is the similar side in the smaller triangle all over the similar side in the larger triangle. That then is equal to the smaller side in the smaller triangle, and let that equal its corresponding side in the larger triangle. So it'll be 74 all over y. Okay, so we've set up a ratio of 2 sets of fractions. We know 3 of the lengths, and the 4th is the y that we're trying to find. Alright, so all we're going to do here to find y is we're simply going to cross multiply. So we're going to get 100y, and that is equal to 9620. Alright, dividing both sides by 100, so y is going to equal 96.2. We're not given centimeters or anything like that, so we're just going to leave it as 96.2. Alright, and filling that in here. I'll fill it in here. Okay, and that's it. Nothing more to it. So this is part 1, and this is part 2. Alright, so again, how do we do questions of this nature? And just I urge you to just have a look at this, rewind and skip the video back to the start of this question, have a look at it again. Right, we have got 2 triangles which are similar. They're not congruent, so they're not the same, but they're similar in that the angles are the same, but the lengths of the sides are different. All right, so the angles are the same, but the lengths of the sides are different. So they are congruent triangles. They're similar, not congruent. All right, so using the fact that you have corresponding sides in the smaller triangle and the bigger triangle, we need to create and set up a ratio of fractions where we have 3 bits of information that we know and 1 that we don't. Use that then to find the fourth, cross multiply and work out for y.